So good morning, everyone. See, yesterday I have introduced about Turing machine and how it works. Okay, so let me just remind you something. Okay, let me use different color here. I'm just circling this one here. Okay. The reason why I'm encircling this one, I'll let you know with another example. So yesterday, what happened? This heights represent whole state. Its heights represent whole state. Okay. Now, in the previous machine, in finite automata, then push down automata, and all we have talked about final states. Remember, once if suppose this is Q naught, this is like this is A. Then after this, we can have like if suppose it's not A, then after A, it starts with another A, then go to reject state. Again, after this A, it move to B, then move to reject state. So by default, if it is not a final state, then we all know that this is a reject state. Okay, and then if A is like currently at Q naught reading A, and then if you're reaching the final state, then we are considering that A is being accepted here. But A is not accepted here, even though I haven't mentioned that this is reject state. So what happened was this is Q naught, Q1, Q2. In the previous example, I'll just take about the finite automata. In the case of finite automata, deterministic automata, what we did, we need to specify that if it is not the final state is being indicated by this double encircling stuff. So if it's not that one, then we know that this is being rejected. Okay. So in the case of Turing machine, right? Yesterday, what I did, I have mentioned a special state which is known as whole state. The difference between whole state and final state is that I won't say whole state is a final state. I will not use the term final state as a whole state or something. I'll just say whole state. What do we mean by whole state? Means this is Q naught, and then if it is whole, then you could not have those A comma B further. If it is whole state, then you have to stop everything there. That's the meaning of that one. So now in the case of Turing machine, right? In the case of Turing machine, if suppose we are going to design a machine which is going to accept a language L, then while designing that machine, right, we should not specify the language, the part of the language which has to be rejected if does not satisfy this language condition. That has to be mentioned here. So from today onwards, right, we are going to instead of heights, right, I'll talk more about this whole state. Instead of heights, you can find in this book, right, Q accept, Q reject. Instead of writing here as heights, you can find after Q naught, you can find Q accept, then Q reject like that. Okay, others rest will be same, and then it will be like Q accept, Q reject like that. And then some textbook, right, they'll say it's a halting state like that. But in my particular definition, I'm not saying this is my version of. I'm not saying this is my version of definition. Today we are going to talk more about this state. So I'm going to talk about this accept state and reject state by considering one example. After understanding that example, right, we'll come back to this particular part. Okay, and then now let me just take one example. Better to take that one. Let me take one example. Now let's design a Turing machine. Let's design a Turing machine. Let's design a TM over 0, 1, which ends with 1. Okay, I'm going to design a Turing machine. Oh, I didn't mention that one. I didn't design a Turing machine which accept the language over this which ends with 1. So let me describe the language which has to be included for designing this Turing machine. 1 will be accepted because it ends with 1. 0, 1 will be accepted. 1, 0, 1 will be accepted. 1, 1 will be accepted. 0, 1, 1 will be accepted. These are the languages needs to be considered. Now, while designing this Turing machine, right? While designing this Turing machine, what we are going to do is, we are going to insert a string inside the input tab. Okay. I have been using hash as the blank symbol. So in my example, I'm using this one as blank symbol. I've already mentioned to specify that one. This one. Now let me insert 1, 0, 0, 1. This ends with 1. Now I'm going to design a Turing machine. While designing that Turing machine, right, I'll start from Q0. If I find this 1 from the input tab, I'll not do anything. Let it be as it is, and then I'll move here towards the right side. If you want to change the state, it's fine. If you don't want, let's see how it will proceed. I don't want to change the state, so let it be as it is. Again, after reading 1 from the input tab, don't do anything. Just move the read write hat on the right hand side of the cell. So let me just do it. So this will be Q0. Again, after reading 0 from the tab symbol, don't do anything. Just move towards the right side. I'm doing that one. Now, after this, if I read 1 from the tab, just move towards right side. Now, after this, right, if you find hash, after this, after this, after this, if you find hash, after this, if you find hash, when I find hash, I'm changing the state to Q1. After finding this hash, what I'm doing is, once you find the hash, come back, come back to the left side or move back to the left side. And then once you find hash, and then if you come back to the left-hand side, the side of the tab, the read-write hat can move towards right side or left side, or you can stay still. So once I find this hash, come back to the left side cell of this particular hash. And if this particular left side cell consists of 1, then accept the string. While designing the Turing machine, which should specify the language which are to be rejected. In our case, we have been asked to design a Turing machine which ends with 1. So what are the possible language to be rejected are 0 to be rejected, 1, 0 to be rejected, 1, 1, 0 to be rejected, 0, 0, 0 to be rejected, 1, 0, 0 to be rejected. These are not the only language, many other categories are there. So this rejection part also needs to be mentioned. Now let me design the accepted part first, and then in that diagram, right, I'll be adding that rejected part. Okay. Now in order to design, let me just rub it. I don't know, sometimes it stuck. I could not delete these things as a whole. That's why I'm rubbing this. I'm moving a little bit slowly, okay, regarding Turing machine, because I don't know, even your senior used to say Turing machine is not very convenient for them. But it's very interesting once you understand the Turing machine. It's a very powerful one. That's why I'm moving a little bit slowly. And then once you understand the designing part and all, it will be very, convenient to design practice for other stuff. Now see here, I'm going to design the diagram. Q naught, initial state. So initial state, what happened? If I read what I was doing, I'll just cut short it a bit. What I was doing is initially I have start reading. I'm scanning the tab from here to here till I find hash. Okay. What I'm doing step by step is from one, whenever you come across 10 or 1 or 0 or whatever, I'm not replacing the tab symbol with any of the new symbol. I'm just leaving this as it is. I'm scanning all the input from the tab one by one till I find this hash. Okay. So now I'll be drawing the diagram here. In the initial state, if I find 0, I'm not disturbing. I'm not replacing this 0 by any of the symbol. I'm just leaving this 0 as it is. And then I'm moving towards right side. Okay. See, in some textbook, you can find a notation like this, this, or this. Okay. Better, this is a little bit, I'm like, I don't find it a little bit neat in my diagram. Okay. So I'm going to follow this pattern. So this one. So if I come across 0, let it be 0 as it is, and then keep moving towards right side. Again, in the same, it's a self loop because there is going to be number, I don't know, n number of zeros and n number of ones. So I could not predict. That's why a self loop. So again, if you've come across 1, leave it as it is, keep moving towards right side. These two are the, I guess, no need to explain much because in a finite automata, I know how you have drawn the finite automata. It's similar to that one. But the way they have written, it's a little bit different here. That's the thing. But concept are same. So it's a self loop here. At the state Q naught, if you find 1 or 0, any number of 1s or 0, do not disturb them with any of the symbol. Just leave it as it is and then keep moving towards right side till you find hash. Okay. Till you find hash. Till you find hash symbol Q1. So if you find hash, what I'm doing is leave it as it is and then move towards left side. Move towards left side. Okay, move towards left side. Now, after this hash, what I'm doing is if I come back to this left side, left cell of this hash, and then if you find 1, then you need to accept it. So I'm doing it. If I find 1 here, if I find 1 here, do not disturb it. Leave it as it is. Whether you want to move towards left side or right side, or you don't want to move anywhere, just right. And then it is final state Q accept. Okay. If the language in the string are combination of zeros and ones and ends with 1, then accept that language. If not, we have to reject. So what are the rejection part? While designing a Turing machine, you have to clearly specify the rejected part also. Rejected part also. Okay. Now regarding this rejected part, right? Now see here, when I start scanning from here, Q naught from here, 1, 0, 0, 1, like that. And then till I find hash, I'm keep on scanning it. When I find hash and then come back to the left cell, instead of 1, if you come across 0, then you need to reject it. Okay. So now I'm going to mention that rejection part here. Instead of 1, if you find 0, then leave it as it is and do not move anywhere. Just reject it. Okay, I'm specifying the term. You might be thinking that this is double circle. This means accepting. Why we are, after reaching the final state, while we are rejecting it, you'll know. Okay, I've clearly mentioned here Q reject. Okay, The final state which we have seen in the case of finite automata, push-down automata, and the final state which we are going to see in the case of Turing machine is a little bit different. In the case of Turing machine, there's a finite set of final states. Among the finite set of final states, we will be having QResec and QAccept. Okay, I'll talk more about this one later on. Let me just complete the diagram. So now, if it ends with 0, then we need to resect it. And then what about this one? What about this one? If it is 0, it begins with 0 and ends with 0, it has to be resected. But what about this one? What about this one? What about the other criteria? Other criteria means if it is 0, let me check this. Let me check the rejection state for this one first. Let me have this one here. If it is 0, hash. This is Q naught. Let me use different color for rejection better. I'm going to check whether my diagram currently, which I have just drawn here, is complete for rejection part or not. I'm going to check for rejection part. Let me just say 0, hash. It will start from Q naught. Currently at Q naught, if it is 0, don't do anything. Just keep moving to it. Right side till you find hash. Now I'm finding hash here. Once you find hash, come back. If it is 0, reject it. So this machine has indicated this one. So let me check for this 1, 0. So let me check for this 1, 0. Let me check for this 1, 0. Let me check for this 1, 0. 1, 0, S. Now it will start from Q naught and then it will start scanning from here to here till we find hash. When you find hash, come back to the left side cell of this hash. If you find 0, reject it. So this is the complete Turing machine for this one. But once we reach here, we cannot we cannot proceed further. That's it. Now this is the Turing machine for accepting a language which is a combination of zeros and ones and then ending with 1. Now, I have inserted two kind of final states. One is QAccept, one is QReject. Okay. Now, let me come back to the part where I have encircle heights. Let me come back to the part where I have encircle heights. Now, regarding this one, right? Let me better. Wait. Let me come back, but I don't have much space here. So I'll just come back here. Now let me tell you, in some textbook, right? Not leave that textbook now. See, instead of H, but the final states which we have seen in the case of other machine and Turing machine is a little bit different because QResect, right? It's kind of halting state, whole state. But once you reach, even though this is final state, but if you reach this part, you have to stop everything and then you have to reject that one. And then regarding this QAccept, right? Once you reach this one this means that it is accepting the thing, but you cannot proceed further. Okay. The main differences of final states between Turing machine final states and other machines lies in here, QResect and QAccept. Now instead of heights here, you'll find like capital heights in some another textbook. So I will not be writing halt here, but in future we are going to deal more about this halting state. Okay, so that's why you need to understand what do we mean by halt state. So now I'm going to insert here QAccept, QResect. or else you can have just finite state of final states. It's up to you. It's up to you. But in every machine which we are going to design, right, we are going to have Q reject and Q accept, and then there might be Turing machine where specifying the rejection part in my machine, the diagram which I'm doing right here, right, need to mention only one criteria for the rejection state. But it may happen that there are like n number of rejection criteria. So anywhere you can insert Q reject part. But when we are inserting Q reject, right, your state diagram becomes a little bit messy. Then you can insert the criteria in the state diagram also, state table also. Okay. So suppose here in this case, right, let me just specify. Let me just clarify it with example. Don't get confused. Let me just specify. Instead of adding the rejection list in the diagram, right, I could have inserted the rejection, right, reject state or rejection list delta q1 0, then q reject 0, and okay, like instead of adding in the diagram, you could specify like this also. Or even though, like, again, no need to mention for rejection list or rejection state, because from the transition function, like you have written Q reject, it means that you're going to reject this one. Okay. In my particular Turing machine, which I'm designing right here, right, in this, I have only a single criteria for adding the rejection list in this particular Turing machine. That's why it's not messy in my diagram. That's why I'm adding this. But you have a choice for designing a Turing machine in future. Either you can modify the state diagram specifying the rejection list like this, or else you can add the criteria in this way also. Okay. This is the simple one. Today I have a BTech project presentation, so I'm just ending the class here. Okay. Tomorrow again, same time at 11 o'clock.